Welcome back to the deep dive. We take the complex, the overwhelming, and the intricate, and we unpack it step by step so you walk away truly well-informed.
And today, we are really getting into it.
We really are. Today, we are undertaking a deep dive into the very foundation of your existence, the human immune system.
And if you're encountering this system for the first time, you really have to set aside the idea that the immune system is, just some autonomous defense force.
Right, like it's a separate army that just lives in your body.
Exactly. Decades ago, researchers pointed out that it is seamlessly and really fundamentally integrated with every other major regulatory pathway. It truly is a complex multi-system.
A multi-system.
Yeah, it's connected by, innumerable structural and functional bridges with the nervous system and the endocrine system. They're all talking to each other all the time.
That's a great starting point for us because it frames this system not as just a wall, but as a central physiological operating principle. Okay, so let's unpack this multi-system. What is its core overriding homeostatic mission?
The central goal is immunity, which just means protection from damage. The concept is ancient. The term comes from the Latin immunis, meaning exempt.
Exempt from public service, I think.
That's the one. And to keep you exempt from disease, the system has one fundamental job that dictates every single action it takes.
And what's that?
Consistently and rapidly distinguishing self, your normal body cells, from everything else, which we call non-self.
And non-self is a massive, massive threat profile. We're talking about invading microbes, viruses, bacteria, fungi.
Plus larger organisms like parasites, environmental threats like allergens.
Right, and also internal threats. This is the one that I think people forget about. Your own cells that have gone rogue, like cancer cells.
Or even just cells that are damaged by trauma. The system has to clean all of that up.
Okay, so when those external defenses, the skin, the mucous membranes, all the things that keep most of the world out, when they fail, the body launches an immediate internal defense response.
It does. And for you, the learner listening right now, a great way to frame this is as a 4-step sequence the body initiates if an intruder crosses that line.
4 steps of internal defense. Step 1, which sounds intuitive, have to be the hardest. We need to detect and identify the pathogen. How does the body even recognize a threat?
It looks for flags. Every pathogen carries an immunogen. That's a substance that is recognized as foreign and therefore triggers the immune response.
Okay, so a flag is detected. That moves us to step 2, communication.
Yes, communication. Because, one cell can't fight a whole colony of bacteria alone. It needs to call for backup.
And how does it do that?
It's heavily dependent on signaling. A lot of this happens chemically, primarily through these little protein messengers called cytokines.
But it's not just chemical signals, right?
No, it also relies on contact-dependent signaling, where one cell's surface receptor literally recognizes and binds to a specific structure on another cell. You can think of it like a complex molecular handshake.
That signaling then moves us to step 3, coordinating that response. So recruiting massive assistance and organizing the attack.
And then step 4, the ultimate physiological goal, destruction. Or, if you can't get complete destruction, then at least suppression and containment of the pathogen.
Can you give an example of containment?
Sure. If you get tuberculosis, for instance, the body often can't destroy the bacteria entirely, but it can be very successful at just walling it off and keeping it contained, sometimes for decades.
Okay, so this internal defense framework is then organized into 2 distinct branches, and they're separated by speed and specificity.
That's right. First up, we have innate immunity.
Innate, from the Latin innatus, or inborn. This sounds like the immediate emergency response team.
It is the rapid response. It's immediate, kicking off within minutes to hours of detection. And this is crucial. It is totally nonspecific.
Nonspecific, meaning what exactly?
It treats a splinter, a flu virus, and a patch of yeast all pretty much the same way. The classic observable sign of this response is inflammation.
That hot, red, swollen area around an injury.
Exactly. And here's a really critical takeaway. Innate immunity involves no memory. You get the exact same response every single time you encounter that threat.
So if I stub my toe today and I stub it again next year, the innate response doesn't remember the first time and speed up.
Nope. It is always starting fresh. Always Groundhog Day for the innate system.
Okay. The counterpoint to that has to be adaptive immunity or acquired immunity.
Yes. This is the highly specialized intelligence service. It is much slower initially, often taking days or even weeks upon first exposure to really get going.
But what does it gain for that trade-off in speed?
It gains extreme antigen specificity. This system learns. It uses specialized, long-lived memory cells for a response that is much quicker, much stronger, and much more focused the second time around.
That distinction nonspecific versus highly specific memory, that feels like the first major physiological principle for you to consolidate.
I think so. And within that adaptive branch, we also divide the labor.
Okay, what are the subdivisions?
We have cell-mediated immunity, which relies entirely on physical contact-dependent signaling. So immune cells have to literally touch their infected targets.
And the other one?
And then there is antibody-mediated immunity. This is often historically called humoral immunity.
If humoral, that's a great piece of context. It connects us back to the very origins of medicine, doesn't it?
It does. It refers to the body's fluids or humors, blood, phlegm, bile from the ancient Hippocratic school.
So because this type of immunity relies on proteins, the antibodies, which are secreted into the plasma and circulate freely in the body's humors, the name just stuck.
That's exactly it.
So those are the organizational mechanics. If we zoom out, the immune system has three major overarching functions that it's trying to juggle all the time, even when we're perfectly healthy.
Right. The three major functions are, first, it acts as an internal quality control system. It recognizes and removes abnormal cells.
Like cells that might have developed mutations leading to cancer.
Precisely. It's constantly policing for internal threats.
Okay, function number two. It acts as a cleanup crew. A city sanitation department, basically.
Exactly. It removes dead or damaged cells and all the cellular debris. And this is a massive job. We're talking billions of old red blood cells that need to be recycled every single day, plus all the general wear and tear in the tissues.
And there are specialized cells for this.
Oh, yes. Specialized scavenger cells patrol the extracellular space, identifying and gobbling up this debris to keep the environment clean.
And the third major function is the one that gets all the attention.
Protecting the body from disease-causing pathogens. This requires coordinating an army of different cell types and molecular weapons against, well, everything from single-celled bacteria to complex parasitic worms. Hashtag tag11. Anatomy and cellular players, ALO 24.2. So to understand how these functions are executed, we have to look at the players and the stage where the action takes place.
And what's so unique about this system is that it's the least anatomically identifiable system in the body. It doesn't have one single dedicated organ like the heart or the liver.
Right. It's an integrated system, not a consolidated one. It's positioned strategically wherever pathogens are most likely to enter or where vital surveillance is required. So in the skin, lining the GI tract, deep within the respiratory system.
And we categorize the tissues based on their function, where immune cells are formed versus where they actually encounter threats.
We start with the primary lymphoid tissues. Think of these as the training academies. They're the sites of cell formation and maturation.
This includes the bone marrow, which is the factory for almost all blood cells.
And the thymus gland.
The thymus, located high up in the chest, is fascinating. This is where T lymphocytes mature. The T is for thymus. It puts T cells through this rigorous education on what self looks like.
And it has a really interesting life cycle. It's largest during adolescence, and then it gradually shrinks. As we age, it often gets replaced by fat tissue.
So after the training academies, we shift to the secondary lymphoid tissues.
Right. This is where the action happens. This is where the mature but still naive immune cells meet the foreign invaders and kick off the adaptive response.
And these tissues are divided into the encapsulated and the unencapsulated.
The major encapsulated tissues are the spleen and the lymph nodes.
The spleen is the largest lymphoid organ. It's like a massive filter for the blood, constantly monitoring for bloodborne pathogens.
And it has another critical job, efficiently removing aging red blood cells from circulation.
And the lymph nodes are miniature biological filters. They monitor the interstitial fluid that's collected by the vast lymphatic circulation network.
So when you feel those tender, swollen glands in your neck during a cold, that swelling is physiological evidence of intense activity.
It's the immune cells collecting and rapidly dividing in the nodes to fight the infection that's been drained from the tissues.
Exactly. Then you have the unencapsulated diffuse lymphoid tissues. These are critical because they're just collections of immune cells aggregated right beneath the surface epithelia, ready to intercept an invader right at the point of entry.
Like in the tonsils or the skin.
Right. These diffuse aggregations are collectively known as MALT, or mucosa-associated lymphoid tissue.
And a huge component of MALT has to be GALT, or gut-associated lymphoid tissue.
Oh, absolutely. The digestive tract has a surface area equivalent to a tennis court. It's massively exposed to the external world through the food we eat, so GALT is essential.
That makes perfect sense. If you think about the constant stream of novel proteins and microbes passing through your gut, it has to maintain the absolute highest level of vigilance.
It does. And the system is so widespread that it's estimated that the total mass of all these specialized cells, the leukocytes, or white blood cells, equals the mass of your entire brain.
Wow. And they're not even that numerous in the blood compared to red blood cells.
Not at all. But their ability to migrate and organize makes them incredibly powerful.
So we have these leukocytes, the primary effectors. How do we categorize this army based on what they look like?
We look at their morphology, specifically the shape of the nucleus and whether or not they contain prominent granules. This gives us the granulocytes and, well, the others.
The granulocytes, basophils, eosinophils, and neutrophils have these visible granules in their cytoplasm, which they forcefully release through a process called degranulation when they get activated.
Yes. The remaining cells, monocytes, lymphocytes, and dendritic cells, are often called agranulocytes, meaning they don't have those big, obvious granules.
Okay, let's break down the functions of the 6 basic types.
We can start with the alarm systems. Basophils and mast cells. Basophils are in the blood, but they're pretty rare. Their more critical relatives, the mast cells, are fixed permanently in tissues, especially the skin, lungs, and GI tract.
They're like strategic sentinels.
Perfect description. When triggered, they release powerful inflammatory chemicals, most famously histamine, which really kicks off the innate response.
Next up, the specialty fighters. Eosinophils.
Eosinophils are also pretty few in circulation, but they concentrate in the epithelia of the GI tract, lungs, and skin. Their job is to defend against large parasitic invaders.
Like hookworms or blood flukes. Things that are too big to just eat.
Right, you can't phagocytize them. Instead, eosinophils attach to the parasite, they coat it, and then they release these highly toxic enzymes and oxidative substances to basically burn or dissolve the invader from the outside.
And they also play a role in allergies, right?
A secondary but very significant role, yes.
Okay, and then we get to the core infantry, the most abundant white blood cell by far. Neutrophils.
Neutrophils make up 50 to 70% of all your white blood cells. They are the shock troops, highly mobile and highly phagocytic.
So they rush to the scene and just start gobbling things up.
They do. They can rapidly ingest and kill about 5 to 20 bacteria during their very short, intense lifespan of just a day or two. Then they die in battle.
And they have a distinctive segmented nucleus, which is why they get the nickname polis.
Correct. And crucially, they also release powerful cytokines, including pyrogens, which are the substances that actively cause fever by resetting the body's thermostat.
Now we move to the cells that specialize in cleanup and long-term surveillance. The monocytes.
Monocytes are the precursors. They only spend about 8 hours circulating in the blood before they migrate into the tissues.
And once they're in the tissues, they change.
They differentiate into these large, powerful phagocytes known as macrophages. Macrophages are the tissue scavengers. They're way more effective than neutrophils, capable of ingesting up to 100 bacteria.
And they clean up the big stuff too, right?
Yes, old red blood cells, dead neutrophils, large debris, they handle it all. Historically, this whole system was called the reticuloendothelial system.
But now we call it the mononuclear phagocyte system.
Right. And related to macrophages are the dendritic cells.
They sound interesting. Named after neuronal dendrites. What's their function?
They're macrophage relatives with these long, highly branched processes. You find them everywhere, including the skin, where they're called Langerhans cells. Their key role is not just to ingest things, but to be the crucial link between the rapid innate response and the slower adaptive response.
So they're messengers.
They are the primary antigen-presenting cells, APCs.
Which brings us to the final type. Lymphocytes. The highly specialized adaptive fighters.
Exactly. Lymphocytes, which include B cells, T cells, and NK cells, are the cells that mediate the highly specific adaptive response. Even though they're only about 20–35% of white blood cells, they are the most important for learning and memory.
Okay, so just to consolidate the functional groups for you, the learner, we have the phagocytes, that's neutrophils, macrophages, and dendritic cells, who ingest material.
And then we have the antigen-presenting cells, APCs, which are the macrophages and dendritic cells, who take fragments of what they ate and display them to the rest of the immune system to say, this is what the enemy looks like. #tag2, development and self-tolerance, LO 24.3.
So this specialization all starts at the very beginning of cell life with a process called hematopoiesis.
Right. All blood cells, every single one, originate from these pluripotent hematopoietic stem cells deep in the bone marrow.
And their differentiation path, what they become, is dictated by chemical signals like colony-stimulating factors and interleukins.
For the lymphocytes, their destination actually determines their specialization. Where they mature is key.
So where do the two major types of adaptive cells mature?
B lymphocytes stay right where they are. They mature in the bone marrow. B is for bone.
Simple enough.
But the T lymphocyte precursors have to migrate. They travel from the bone marrow to the thymus gland T for thymus, for their very extensive maturation and education process.
And we also mentioned natural killer NK cells as a third category of lymphocyte. They're interesting because they function in the innate rapid response, acting as a kind of bridge between the two systems.
They do. Now let's talk about the incredible complexity of the adaptive response, which is specificity. There are millions of possible threats out there, so the body needs millions of possible solutions.
And the way it does this is that each individual B cell and T cell has membrane receptors specific to only one particular antigen.
Correct. All the cells that are specific to that one antigen form a distinct group called a clone.
This sounds like a massive storage problem. If you need a unique blueprint for every single possible enemy, how do you manage that inventory?
The body's solution is brilliant, really. It maintains millions of different clones, but it only keeps a few cells, the naive lymphocytes of each clone on hand. They're just on standby.
So when a matching pathogen shows up,
That small clone is rapidly activated and reproduces millions of copies of itself. That's a process called clonal expansion, and it provides the necessary, highly specific army you need.
but before that army can fight, they have to pass the ultimate loyalty test, which is the system's ability to prevent friendly fire. This is self-tolerance.
This is absolutely non-negotiable. The lack of an immune response to the body's own cells is self-tolerance, and it's a prerequisite for survival.
And this is developed early during embryonic development through a really rigorous selection process.
It is. It happens in the primary lymphoid tissues. So let's walk through the cause and effect. The lymphocytes acquire their unique receptors randomly. We keep the ones that do not recognize any self-antigen.
So those are the ones allowed to live and form the body's defense clones.
Right. Conversely, if a lymphocyte develops a receptor that does bind strongly to any self-antigen present in the bone marrow or
I
thymus,
think it's eliminated.
immediately, that cell is targeted for destruction by apoptosis-programmed cell suicide. This ruthless removal process is called clonal deletion or negative selection.
And that's what prevents self-reactive clones from ever reaching maturity and causing an autoimmune disease.
When it works, yes, that's the goal.
That system is designed to be fail-safe,
Mm-hmm.
but when it fails, the results are obviously devastating.
They are. And, speaking of developing immunity, we should probably touch on the hygiene hypothesis. It offers a really fascinating perspective on how our modern environment affects this whole training process.
Right, this is the observation that as developed countries achieve massive success in eradicating parasitic, viral, and bacterial diseases,
Through public sanitation and medicine, yeah.
we've simultaneously seen this dramatic increase in autoimmune and allergic diseases, things like type 1 diabetes, asthma, and food allergies.
The hypothesis suggests that early exposure to pathogens, or even just benign microbes, helps to train and calibrate the immune system.
So a too clean environment means the system doesn't get the challenges it needs to properly learn the difference between real threats and harmless things like pollen.
In essence, yeah, it's like the system gets bored and starts misfiring. Some theories suggest the problem is even more specific.
What do you mean?
There's the worm theory, for example. It suggests that the lack of exposure to old parasitic infections is key. Those infections typically cause the body to generate huge amounts of regulatory T cells to suppress the inflammatory response.
And without those complex challenges, our regulatory mechanisms aren't strong enough.
Yeah.
And the system just overreacts to minor irritants.
Exactly. It's a profound area of research really focused on our changing relationship with the microbial world around us. #3. Molecules of the innate immune response, LO 24.4.
Okay, let's pivot from the cells and the training to the immediate arsenal of chemistry, the molecules of the innate response.
These are molecules that are either always present in the plasma or they're secreted so rapidly upon a challenge that they define that instantaneous response.
And we can group these innate chemicals into functional classes that govern what happens first.
Right. First, you have the chemotaxins.
What's their purpose?
They are chemical signal molecules. They could be bacterial toxins, or they could be endogenous damage signals. Bits and pieces of fibrin or collagen that are created when tissue is injured. We call those DAMPs for danger-associated molecular patterns.
And their role is just to attract help.
That's it. They create a chemical breadcrumb trail, attracting phagocytes like neutrophils and macrophages straight to the infection site.
Okay. Next are the opsonins. I love that the root means to buy provisions. It really sounds like they're making the meal ready.
They do just that. Opsonins are molecules that coat foreign particles, essentially making them highly visible food for phagocytes. They dramatically enhance recognition and ingestion.
So if a bacteria is slippery or has a capsule, opsonins act like molecular handles that the phagocyte can grab onto.
Perfect analogy. And finally, in this group, we have pyrogens.
Pyrogens are fever producers.
Yes, primarily cytokines released by activated leukocytes. They don't heat the body up directly. They communicate with the thermoregulatory center in the hypothalamus and alter the body's temperature set point upward, which is what initiates the fever.
Okay, now for the specific chemicals, and there's quite a list, let's start with the immediate responders produced by the liver. The acute phase proteins.
These are proteins that rapidly increase in concentration in the blood right after an injury or invasion, so during the acute phase.
And what do?
Several jobs. They can act as opsonins or as enzyme inhibitors to prevent excessive tissue damage from our own immune enzymes. The one that's most commonly measured clinically is C-reactive protein, or CRP.
And why is CRP so important for you, the learner, to remember?
Because it's a powerful opsonin that activates complement, but also because elevated CRP levels are highly significant beyond just acute infection. They're linked to chronic inflammation and are now recognized as a key risk indicator for coronary heart disease.
So it suggests a low-grade immune activation is happening continuously.
That's the idea. Now, the primary molecule that initiates the classic physical signs of inflammation is histamine.
And that's released instantly from the granules of mast cells and basophils.
Yes, during degranulation. And its action is, well, it's physiological genius for defense. It performs two key actions crucial for recruiting health. First, it causes vasodilation in the area, increasing blood flow.
Which causes the redness and heat you feel.
Exactly. And second, and this is critical, it increases capillary permeability by opening up the pores in the capillary walls.
Allowing what to happen?
This allows plasma proteins, which are normally way too large to get out of the circulation, and water to escape rapidly into the interstitial space.
And that influx causes the tissue edema, or swelling, which can be painful because it presses on nerve endings.
Right, but that swelling is essential. The fluid brings in clotting factors and other plasma proteins that help wall off the infection site.
Okay, so now the action gets structural. The complement proteins. This is a group of over 25 plasma and cell membrane proteins that operate like a highly specialized chemical cascade.
Very similar to how blood coagulation works, yes. When it's activated, the intermediate products of this cascade act as highly effective opsonins, chemotaxins, and they also trigger more mast cell degranulation.
But the truly destructive non-cellular weapon of the innate response is the end product of this cascade, the membrane attack complex, MAC.
That MAC is a literal chemical drill bit. It's a group of lipid-soluble proteins that get assembled one by the cascade. They insert themselves into the membrane of a pathogen, and they form these giant, gaping pores.
And because it's purely a cascade of proteins, no living immune cells are needed for the killing action itself.
That's right, and the result is immediate rupture-lysis. Water and ions rush in through those new pores, the cell swells up, and bang, it ruptures. It's a quick, efficient chemical switch.
And it works particularly well against unencapsulated bacteria.
It does. We also have interferons, IFN, which are protein cytokines known for, well, interfering with viral replication.
So when a cell gets infected, it releases interferons to warn its neighbors.
Exactly. It causes the neighboring uninfected cells to make internal antiviral proteins that will inhibit the virus from replicating if they get invaded later.
Then you have the general messengers, interleukins, IL.
Interleukins are a broad category of cytokines secreted by leukocytes that mediate inflammation. Interleukin-1, for example, is a common pyrogen that induces fever.
And we should also mention lysozyme, an enzyme in our secretions that attacks bacterial cell walls.
And tumor necrosis factor, TNF, a cytokine that promotes inflammation and can also cause cells to destroy themselves via apoptosis. #tag4, antigen presentation and adaptive recognition, LO 24.5.
All right, so the adaptive specific defense can't move until the innate system shows it the target. This pivotal communication step is called antigen presentation.
And this presentation relies entirely on the Major Histocompatibility Complex, MHC proteins. These are highly specific membrane protein complexes whose sole job is to grab internal or ingested antigen fragments and display them visibly on the cell surface.
Okay, let's break down the two classes of MHC because their location totally dictates their function. Where is MHC class I found?
MHC class I molecules are found on every single nucleated cell in your body.
Every cell with a nucleus.
Exactly. So think of MHC class I as the cell's universal status report, displayed for specific T cells to read, and if the cell has a brain, it's posting its status.
So if a cell is infected by a virus, it uses MHCI to broadcast the warning, help, I'm compromised.
Precisely. Now, MHC class II molecules are different. They are found primarily on the antigen-presenting cells, APCs, so macrophages and dendritic cells.
So MHC class II is like the APC's trophy case, showing off what it killed and ate.
That's a perfect analogy. The function of both classes is to combine with digested antigen fragments inside the cell. The entire complex is then inserted into the cell membrane, making the antigen visible on the outside, accessible to the T lymphocytes.
And it's critical that free antigen can't just bind to an empty MHC receptor, right?
Yep.
It has to be processed and presented by the host cell.
That's a key point, yes.
I understand that these MHC proteins are so individually unique that they cause major clinical issues in transplants.
They are. Clinically, they're known as human leukocyte antigens, HLA. Because they're inherited with massive variation, it's highly unlikely that any two people, barring identical twins, show the exact same set.
And that extreme variability is why the recipient's immune system will see donated tissue as non-self and launch a massive tissue rejection response.
That's the heart of the problem, yes.
Okay, now we move to the recognition molecules that actually initiate the specific fight. We have two key players here.
First, the T cell receptors. These are membrane proteins on T lymphocytes. And you have to remember, T cells only recognize antigen when it's presented by MHC complexes.
They're contact specialists. They have to literally touch the MHC antigen complex on the surface of another cell to get activated.
Right. And they are not antibodies.
In contrast, B-cell antibodies, or immunoglobulins, IG, are designed to work in the fluid phase.
Correct. They're proteins produced by B lymphocytes and secreted by their descendants, the plasma cells. They bind to free-floating antigen in the extracellular fluid in the blood, lymph, and tissue spaces, and they make those antigens visible for the rest of the immune system to find and destroy.
And if we look at the antibody structure, it's just a physiological masterpiece. It's a classic Y-shaped molecule.
Built from 4 polypeptide chains, 2 identical light chains, and 2 identical heavy chains, all held together by disulfide bonds. And that Y shape has 2 main functional areas.
The arms of the Y are the Fab region.
Yes, and that contains the 2 highly specific antigen binding sites. This is the variable region that provides the specificity that is the hallmark of adaptive immunity.
And the stem of the Y is the FC region.
The FC region is the constant region. This is what determines the antibody class, IgG, IgM, and so on. And crucially, this is the part that binds to immune cell receptors, signaling to a phagocyte or mast cell what action needs to be taken.
Okay. To make the 5 major immunoglobulin IG classes more memorable, let's give them nicknames based on their primary function.
A good idea. We have to start with IgG, nickname, the long-term defender.
And this is the most abundant one, right? About 75% of plasma antibody.
It is. And why is it key? Because it's the only class that's small enough to cross the placenta. It provides essential passive immunity to infants for their first few months of life. It also activates complement very well.
Next, IgA, nickname, the mucosal protector.
IgA is found in all your external secretions, saliva, tears, mucus, breast milk. It protects external surfaces by binding to pathogens right at the entry point, flagging them for removal or preventing them from sticking to your cells.
Okay, IgE, nickname, the allergy alarm.
IgE targets large parasites, but it's notorious for its role in allergic responses. It binds very strongly to mast cell receptors, so when an allergen later binds to that IgE, it triggers rapid degranulation and the release of all that histamine.
IgM, nickname, the early responder.
IgM is the first antibody produced during a primary immune response, which makes it a great early marker of an infection. It's a fantastic activator of complement.
And it's also the class that reacts to the antigens on red blood cells in ABO incompatibility.
It is. And finally, IgD nickname, the D cell activator.
So its job is mostly on the B cell itself.
Yes. It appears as receptors on the B lymphocyte surface, and its main role is just to help activate the B cell to start the process of differentiation and clonal expansion. #5. Pathogens and barriers. LO 24.6, 24.7.1. So before we detail the defense strategy, we have to understand the enemy. While we face all sorts of things, the most prevalent infections in the modern world are viral and bacterial.
And the body needs to use fundamentally different defense mechanisms for each, primarily because of their basic structure and where they live inside the body.
Exactly. Bacteria are true cells. They have their own metabolism, usually a cell wall, sometimes a protective capsule. Most can survive and reproduce perfectly well outside of a host cell.
And because they're living cells with their own internal metabolic pathways, they can be killed or suppressed by antibiotics, which target those specific pathways.
Right. In stark contrast, viruses are not cells. They are essentially just packets of nucleic acid, a blueprint, either DNA or RNA wrapped in a protein coat called a capsid.
And they are obligate intracellular parasites.
Which means they must invade a host cell and hijack its machinery in order to replicate. This makes them totally immune to antibiotics.
And it means the immune system can only eliminate them by resorting to a physiological scorched earth policy, destroying our own infected host cell.
Which is the domain of cell-mediated immunity, yes. That viral replication cycle is the central problem. Once the virus gets inside a host cell, it takes over the cell's resources to make new viral particles. Some kill the cell immediately, some hide out for years.
So understanding the target is step one. Step two is really appreciate the effectiveness of the body's first line of defense, the barriers. If these physical, mechanical, and chemical barriers work, the complex internal immune response is totally unnecessary.
The physical barriers are the skin, a tough multi-layered organ, and the protective mucus linings of the digestive, genitourinary, and respiratory tracts.
And given the thin, delicate epithelia you need for absorption or gas exchange, the digestive and respiratory systems are inherently the most vulnerable entry points.
They are. Then you have the mechanical barriers. These are the flushing mechanisms. The respiratory tract uses the mucociliary escalator.
A constant upward wave of mucus and cilia that traps and transports particles and microbes up the throat to be swallowed or expelled.
Right. And we also rely on tears, coughing, sneezing, and even the rapid flushing of the GI tract during secretory diarrhea to mechanically expel invaders.
And finally, the chemical barriers. These are the specialized secretions.
This includes enzymes like lysozyme found in saliva, tears, and respiratory secretions, which specifically attacks the cell walls of unencapsulated bacteria.
And you've also got the extremely low pH of stomach acid and the presence of IgA antibodies in external secretions, providing constant surveillance. Tag 6, innate immune response mechanisms. LO 24.7.2.
So if the barriers are breached, the rapid, nonspecific innate immune response kicks in. The genius of its speed lies in its broad specificity. It doesn't need to identify the exact strain of bacteria.
It just needs to recognize general PAM-Ps, pathogen-associated molecular patterns, that are unique to large groups of microorganisms, like a piece of a bacterial cell wall.
Exactly. So let's trace the initiation. Once PAM-Ps, or the tissue damage signals, the DAMPs, appear, they immediately trigger chemotaxis.
Which is the guided chemical attraction of leukocytes. So the white blood cells in circulation get the signal and have to leave the blood vessels to get into the tissue.
A process called extravasation, where they literally squeeze between the pores of the capillary endothelium to get to the site of infection.
And the relentless flood of neutrophils and macrophages fighting this battle is what produces pus.
Which is, yeah, essentially a collection of living and dead leukocytes, ingested debris, and tissue fluid, the residue of a highly active innate response.
So the central action on the front line is phagocytosis, carried out mainly by macrophages and neutrophils.
And this is a receptor-mediated event which ensures efficiency. The cells aren't just ingesting random fluid, they're actively targeting specific particles.
Okay, let's follow the 4 steps of ingestion and destruction for you, the learner. Step 1. Pathogen PAM-Ps bind to the phagocytes' surface pattern recognition receptors, PRRs.
Step 2. The phagocyte uses its internal scaffolding, actin filaments, to rapidly surround the particle, enclosing it in a little membrane-bound sac called a phagosome.
Step 3 is the cellular kill step.
Right. The phagosome fuses almost instantly with the cell's powerful internal garbage disposal unit, the lysosomes.
And those lysosomes contain the chemical weapons.
They do. Potent digestive enzymes, but also extremely reactive. Oxidizing agents like hydrogen peroxide and the superoxide anion. This is often called the respiratory burst.
So step 4. These chemicals just digest the organic pathogens, breaking them down into little antigenic fragments.
That's the process. But it's important to remember that even this robust innate system can be fooled.
Right. Some encapsulated bacteria have evolved a thick capsule that effectively masks those PMPs.
So the PRRs can't see them. For these pathogens, immediate ingestion is impossible until they are coated by opsonins, either complement proteins or antibodies, which allows the phagocyte to finally recognize the threat.
Okay, let's talk about the innate lymphocytes. Natural killer NK cells. They are so vital because they provide an immediate early defense against one of our most common systemic threats, viral infections.
NK cells act incredibly fast, within hours, and they're designed to force virus-infected cells to commit suicide via apoptosis.
And their recognition mechanism is particularly clever. They don't look for the virus itself, they look for cells that are trying to hide.
How does a cell try to hide from the immune system?
By taking down its status report. Viruses often try to evade the cytotoxic T cells by blocking the host cell's synthesis of MHC class I proteins.
So if the infected cell stops displaying MHC class I, the T cells can't see the viral antigen inside.
But the NK cells recognize this absence of MHCI display as a red flag. It doesn't matter what antigen is or isn't there, they attack the cell that is failing to wave its flag.
It's a brilliant backup system. Finally, let's just revisit inflammation, the hallmark of innate immunity. We know the signs: redness, heat, swelling, pain. But what are the three essential physiological roles it serves?
Its roles are threefold. First, attract immune cells and mediators to the area. Second, produce a temporary physical barrier with clotting and edema to physically slow the spread of the pathogen.
And third, to promote the eventual tissue repair once the threat is neutralized. And all of these effects are driven by that cascade of chemicals we discussed earlier: the vasodilation, the increased permeability, and the pyrogens. Check 7. Adaptive immune response mechanisms. LO 24.7.3, 24.7.4, 24.7.6.
May we make that crucial physiological link, the handover from the rapid, nonspecific innate response to the slower specific adaptive response. How did the scavengers of the innate system communicate the threat?
This is the whole purpose of the antigen-presenting cells, APCs. Macrophages and dendritic cells, after they ingest and digest a pathogen, they take those little antigenic peptides and combine them with their specialized MHC class II proteins.
And that MHC-TII antigen complex gets inserted back onto their cell membrane. So the APC has gone from a scavenger to an intelligence courier.
That's a great way to put it. The dendritic cells, in particular, then leave the site of infection and migrate specifically to the secondary lymphoid tissues, like the lymph nodes,
Where they present the antigen and activate the waiting, naive lymphocytes.
Yes. And once that antigen is presented, the highly specific defense begins with clonal expansion.
Okay, walk us through what that looks like.
It's the rapid reproduction of the one or two naive lymphocytes whose receptors just happen to match the presented antigen. This first exposure activates the clone and stimulates rapid division.
And this division creates two crucial groups of daughter cells.
Right. You get short-lived effector cells that carry out the immediate battle and then die off. And you get long-lived memory cells that remember the exposure and reproduce constantly to maintain a low vigilant number.
The result of this first activation is the primary immune response. It's slow to start, takes days, and produces a pretty low magnitude of antibodies.
But the body has paid the learning cost. The second exposure triggers the secondary immune response.
And the memory cells activate rapidly, leading to incredibly fast clonal expansion and antibody production at prodigious rates.
We're talking up to 2,000 molecules per second per plasma cell. The defense is faster, stronger, and just overwhelming.
Okay, let's focus on the first adaptive cell type, B lymphocytes and their role in humoral immunity.
Naive B cells are born with up to 100,000 antibody-like receptors on their surface. When that B cell receptor binds to its specific antigen, the B cell is activated.
And the activated B cells then rapidly differentiate into the two functional subtypes.
Plasma cells and memory B cells.
The plasma cells are the factories.
They are. They quickly lose their surface receptors and they dedicate their entire existence to synthesizing and secreting soluble antibodies, the immunoglobulins, into the plasma.
And most of these plasma cells are short-lived, dying after the threat is controlled.
Right, but a small subset becomes long-lived plasma cells, migrating to the bone marrow and continuously secreting low levels of antibody for continued, sometimes decades-long, immunity.
This is a critical point for you, the learner. Antibodies don't directly kill anything. They are tags and organizers. So what are the main functions of an antibody once it binds to an antigen?
They primarily disable or make the threat visible. First, they cause antigen clumping or agglutination. Because an antibody has two binding sites, it can bridge two antigen particles, linking them together like a bunch of grapes.
Which prevents them from spreading and makes the whole clump an easier target for scavengers.
Exactly. They also handle the toxins. They can inactivate bacterial toxins by binding directly to the active sites of those toxins, neutralizing their destructive effects.
And third, they act as powerful opsonins.
They coat the immune complex, and phagocyte receptors recognize the Fc region, the stem of the antibody, and just ingest the entire tagged complex.
They can also trigger the innate system.
Yes, they trigger degranulation of mast cells or NK cells. They activate complement proteins, assisting with that MIC formation. And finally, they continue to activate B lymphocytes themselves to make sure the factory keeps running.
Now to the contact-dependent specialists. T lymphocytes and cell-mediated immunity. These are the critical defense against intracellular pathogens like viruses.
T cells are fundamentally different because they must have the antigen presented to them on an MHC protein. We have three crucial subtypes here.
First, the assassins. Cytotoxic T.
CyTC cells attack and destroy virus-infected host cells that are displaying viral fragments via their MHC class I complexes. They essentially perform state-sanctioned execution of our own cells.
So they have two mechanisms to do that?
They do. Mechanism 1 involves chemical pore forming. They release two substances, perforin, a pore-forming molecule, and granzymes, which are cytotoxic enzymes.
So perforin punches holes in the target cell and the granzymes go in through the holes.
And activate an enzyme cascade inside that commits the cell to apoptosis.
And mechanism 2 is direct contact, the death receptor.
They activate a protein called Fas, a death receptor on the target cell membrane, which triggers the exact same apoptosis enzyme cascade. The end goal is the same: sacrifice the infected host cell to prevent the replication and spread of the invader.
Next are the generals, the conductors of the entire specific response, helper T.
Cells. Taxotiles don't kill anything directly. They bind to antigen presented on MHC complexes on APCs. Once they're activated, they secrete a massive variety of powerful cytokines that orchestrate the entire immune system.
They stimulate B cells, they stimulate TEXIOs, they enhance macrophage activity. They're the essential coordinating link.
They are, and the critical relevance here is why diseases like HIV are so devastating.
Because HIV preferentially infects and destroys TEXIA cells.
Right. It essentially eliminates the master coordinator. Without the TEXT cells, B cells and TEXIA cells largely fail to receive the chemical stimulation they need to launch a vigorous, effective defense.
And finally, we have the police, the peacekeepers, regulatory T cells.
They also bind to MHC2 complexes, but they release cytokines that specifically suppress the immune response. They are crucial for dampening the system once the threat is neutralized, preventing excessive collateral damage to our own tissues.
So as a quick summary before we integrate these responses, active versus passive immunity.
Passive immunity is quick but temporary. It's when you acquire antibodies made by someone else, like maternal IgG to a fetus, or an injection of gamma globulin. The protection only lasts as long as those antibodies survive, maybe 3 months.
And active immunity is long-term. Your body produces its own antibodies after exposure, either naturally through an infection or artificially via vaccination.
Which primes the system by triggering the creation of those memory cells, but without causing the disease itself. #8, integrated immune responses, L24.8.
We have all the pieces. Now let's put them together using the two most common scenarios. First, the response to a classic extracellular bacterial infection.
Okay, this is primarily a defense that relies on fluid phase weapons and phagocytes. Step 1 is the rapid, nonspecific attack, mainly involving the complement system activation.
And how fast is that?
It starts within minutes. Bacterial cell wall antigens activate the cascade. The products immediately act as opsonins, chemotaxins, and triggers for inflammation. If the bacteria are unencapsulated, the MAC can form and cause lysis right away.
Step 2, phagocytes.
Macrophages and neutrophils arrive and immediately start ingesting any unencapsulated bacteria. If the bacteria have that protective capsule, this is where the opsonins, the complement products or early antibodies become mandatory. They have to coat the capsule first.
And step 3 is the adaptive response kicking in days later to sustain the fight.
Right. APCs activate TEXT cells, which then activate naive B cells. This leads to clonal expansion, plasma cell antibody production, and memory B cells. The secreted antibodies then become powerful opsonins, dramatically boosting phagocytosis, and they neutralize any bacterial toxins being released.
Okay, the response to a viral infection is a completely different two-pronged strategy focus on intracellular defense.
It is. A virus has an extracellular phase and an intracellular phase, so it needs different weapons. In the extracellular control phase, pre-existing antibodies from a prior infection or vaccination quickly neutralize the viruses.
They act as opsonins and prevent the viruses from infecting new host cells. But once the virus is inside a cell, those antibodies are useless.
Totally useless. That's why the APCs and T cells are so vital. The APC role takes center stage. Macrophages ingest the viruses, insert viral fragments into their MHC2, and secrete powerful cytokines, including interferon alpha.
Which alerts the neighboring cells to start making antiviral proteins.
Exactly. Then the T cells see that MHC2 complex on the macrophage. They become fully activated and secrete a massive flood of cytokines.
And this stimulates the entire defense. You get a humoral boost where memory B cells become plasma cells and pump out more neutralizing antibodies.
And most importantly, you activate the intracellular attack force.
Which is the domain of the T cells.
Correct. The activated cytotoxic T cell patrol the body looking for any cell broadcasting that viral antigen on its MHCI complex. When they find one, they destroy it using perforin and granzymes, inducing apoptosis and stopping viral replication.
And at the same time, the NK cells act as backup, attacking any infected cell that tries to hide by suppressing its MHCI expression.
It's a beautifully coordinated, multi-layered attack.
The physiological takeaway here is that viruses force the body to destroy its own infected cells in a controlled way to achieve long-term survival.
Exactly. And this defense is constantly challenged by the ability of certain viruses like influenza or HIV to mutate rapidly. They change their protein code, their primary antigen.
Which means the antibodies and memory cells from a prior strain may no longer recognize the new strain, which is why we need new flu shots every year.
Precisely.
Okay, let's look at a case of misfiring. Allergic reactions or hypersensitivity. This is an inflammatory response to a non-pathogenic antigen and allergen.
And the body creates this inappropriate over-the-top response. The most common is immediate hypersensitivity, which is mediated by IgE antibodies and happens within minutes. It's a two-act play. Sensitization and re-exposure.
Walk us through the sensitization phase.
Upon first exposure, APCs ingest the allergen, activate the TEXA-H cells, which in turn activate B lymphocytes. The B cells then produce IgE antibodies specific to that allergen.
And critically, these IgE antibodies then migrate and bind firmly to mast cell receptors all over the body, creating a fully sensitized, primed system.
Right. So the danger is not the first contact, but the re-exposure.
Upon re-exposure, the allergen binds to the IgE that's already fixed on the surface of the mast cells.
And this triggers massive, rapid degranulation all across the body, releasing huge amounts of histamine, leukotrienes, and prostaglandins. This explosion of chemicals causes widespread vasodilation, leakage, and bronchoconstriction.
Which leads to swelling, hives, and respiratory distress.
And the most extreme form of this, anaphylaxis, is life-threatening because that widespread degranulation causes a catastrophic drop in blood pressure and circulatory collapse combined with severe bronchoconstriction.
Finally, let's quickly look at transfusion reactions. Red blood cells lack MHC proteins, but they have other antigens, mainly the ABO and Rh groups.
The ABO blood groups are defined by the A and B glycoproteins on the RBC membrane, and your plasma naturally contains antibodies to the antigens that your body lacks.
So if I have type O blood, I have neither A nor B antigens, but I have both anti-A and anti-B antibodies ready to attack any other blood type.
Exactly. So if you, a type O person, mistakenly receive type A blood, your anti-A antibodies will bind to the donor RBCs, causing mass agglutination or clumping.
And this clumping immediately activates complement, forms the MAC, and causes lysis, releasing free hemoglobin into the circulation.
Which can cause acute kidney failure. It highlights the absolute necessity of blood matching.
And the Rh blood groups involving the D antigen are most critical in hemolytic disease of the newborn.
Right. If an Rh mother carries an Rh plus fetus, leakage of fetal blood at birth can trigger her immune system to produce anti-D antibodies. In a subsequent pregnancy with another Rh plus fetus, those anti-D antibodies can cross the placenta and attack the fetal RBCs, causing severe destruction. #tag9. Immune system pathologies, LO 24.9. So immune system failures generally fall into three categories: incorrect, overactive, or a lack of response.
And the most profound failure is the incorrect response. Autoimmune disease, which is the failure of self-tolerance. The body makes antibodies or launches cytotoxic attacks against its own components.
These diseases are often restricted to a specific organ or tissue. In type 1 diabetes, it's the destruction of pancreatic beta cells. In Graves' disease, antibodies mimic TSH and overstimulate the thyroid.
And in multiple sclerosis, T cells attack the myelin sheath around neurons in the central nervous system. Why does self-tolerance, which is based on that clonal deletion, fail?
The leading hypothesis is cross-reactivity. The idea is that the body encounters a foreign antigen, a bacterium, maybe, that just happens to be molecularly similar to a human self-antigen.
So the body successfully makes antibodies to the foreign invader. But those same antibodies then recognize and damage our own human tissue because of that molecular similarity.
That's the theory. And treatment often involves high-dose glucocorticosteroids like cortisol derivatives, which suppress general immune function.
Related to incorrect responses is the hypothesis of immune surveillance.
This is the idea that cancer cells are forming regularly, maybe hundreds of times a day, but they're detected and destroyed by the immune system often before they can ever establish a tumor.
So the NK cells and T cells are acting as constant sentinels, just editing out defective cells.
Exactly. They recognize that some cancer cells, like virus-infected cells, may fail to display normal MHC antigens, which flags them as abnormal and targets them for destruction.
The second category is overactive responses. We covered these with allergies and hypersensitivity, where the response is just way out of proportion to the harmless nature of the antigen.
And the third category is a lack of response. Immunodeficiency diseases. This is when a component of the immune system fails entirely.
And this can be primary immunodeficiency, so genetically inherited disorders.
Or acquired immunodeficiency, which can result from an infection, like the destruction of TH cells by HIV/AIDS, or from the side effects of medical treatments like chemotherapy or radiation therapy. Hashtag tag10. Neuroendocrine immune interactions. 10024.60.
We started this whole deep dive by calling the immune system a multisystem. And this final section really drives that concept home by detailing the complex communication network linking the immune, nervous, and endocrine systems.
This field is known as psychoneuroimmunology, or PNI. For decades, science tended to separate these systems, treating the immune system as if it were autonomous.
But we now know that emotions and psychological states are intimately linked to our physiological defense mechanisms. There's constant bidirectional communication between all three systems.
And the communication is possible because they all speak the same chemical language.
They share signal molecules and receptors.
They do. Immune cells are known to secrete hormones once thought to be exclusive to the endocrine system, like ACTH or TSH. Conversely, neurons in the brain have receptors for immune cytokines. Even NK cells have opiate receptors that are all listening to each other.
And because they talk, they can modulate each other. How do the neuroendocrine signals impact the immune system?
This is where we see the direct impact of stress. Increased levels of the stress hormone cortisol are directly linked to immune suppression.
So cortisol decreases antibody production, it depresses lymphocyte proliferation, and diminishes NK cell activity.
All of the above. And we also see neuropeptides like substance P, which is involved in pain sensation, directly inducing mast cell degranulation.
And on the flip side, the immune system also talks back to the brain and the glands.
Absolutely. Cytokines from the immune system can affect neuroendocrine function. When you have a pathogenic stressor, like a serious infection, immune cytokines like interleukin-1 can travel to the brain and induce CNS stress responses.
Which is the physiological basis of sick misbehavior, feeling tired, lethargic, not wanting to eat.
Exactly. So the clinical reality is that stress alters immune function. Stress, defined as any nonspecific stimulus that disturbs homeostasis, elicits an organized response.
And while acute stress triggers a rapid, adaptive fight-or-flight response, it's the chronic or repetitive stress that is so physiologically damaging.
Prolonged stress leads to persistently elevated cortisol levels, and that results in the associated suppression of the immune system, which leaves the body more vulnerable to pathogens.
The complexity of PNI lies in integrating psychological perception with molecular biology. But the simple recognition of this mind-body connection has paved the way for complementary therapies like meditation, yoga, and biofeedback.
And yes, the idea that humor and laughter may actually increase immune cell activity is being actively studied, suggesting that mental and emotional stimuli are truly integrated through the CNS and directly influence our physiological defenses.
So what does this all mean for you, the learner? We have synthesized a massive overlapping set of defense mechanisms, from a single B-cell clone to the systemic effects of cortisol.
The key synthesis, I think, is this. The immune system maintains homeostasis by first achieving that crucial distinction of self from non-self. It relies on a rapid, nonspecific innate defense barriers, phagocytes, complement inflammation, to immediately contain a threat.
And that innate response is then amplified and sustained by the slower, highly specific adaptive response, which is mediated by targeted lymphocyte clones, secreted antibodies, and that critical cell-mediated attack on infected cells.
And the entire coordination hinges on chemical communication via cytokines and the critical antigen presentation machinery of the MHC proteins.
So here is the truly integrated complexity we started with. The neuroendocrine immune axis means that physical stressors like a severe viral invasion and psychological stressors like intense chronic anxiety both feed into the same chemical pathway.
Resulting in a measurable biological effect via cortisol-suppressing lymphocyte and antibody activity.
Your emotional state has a direct and measurable impact on your ability to fight disease. That interconnectedness is the ultimate physiological marvel.
Absolutely. The system is a masterwork of complexity.
As a final provocative thought for you to explore on your own, consider the question we raised earlier about IgA antibodies. We noted that they are massive proteins, yet they become part of external secretions like tears and saliva, which are outside the normal circulation.
So if large proteins are fundamentally too big to simply diffuse across cell membranes, how does the body actively cheat the size limits of the cell membrane?
How does it transport these critical antibodies across the epithelial layers into external secretions? Think about your knowledge of cellular transport and epithelial function and how that might apply to the immune system's massive need for delivery.
A great challenge to integrate the knowledge. Thank you for joining us on this deep dive.
We appreciate you tuning in. Until next time.